Today we are going to talk about reflection and transmission via potential barrier. Let me tell you first in the beginning of the lecture that this is not a complete lecture. It is actually the synopsis of the lecture because of the technical limitations we have here. Before I begin my lecture, let me ask you a simple question. If a ball travels parallel to the ground and hits a wall 20 feet high, what do you expect to happen? Obviously, it will be reflected. Quantum mechanics is also in agreement with this fact, but only when the wall is infinitely high. What in the case of less formidable wall? Quantum mechanics differs here. There is always a finite probability that the particle will be reflected as well as transmitted through the barrier. This is what we are going to explore today. We take a beam of electrons. To save the time, actually, I have written all the derivations in the beginning only, and I'll be explaining each step actually. We have a stream of electrons having energy E, which is incident on this potential barrier you can see, whose height is V and the width is L. We have to explore what is the probability of reflection of the electron beam and transmission of the electron beam. For the purpose, we first define the potential function of this problem. And you can see there are three regions: region number 1, region number 2, and region number 3. Region 1 is to the left of the barrier, region 3 is to the right of the barrier. Electrons are incident from the left and they are initially in the region 1. As in the region 1, electrons are free, the potential energy will be 0, no force is acting on the electrons. And same for the region 3, and therefore the potential function for the problem is this: be x equals 0 for x is less than equal to 0 and x is greater than equal to L. Whereas for the region 2, we have the potential function given as Vx equals V for 0 less than x is less than L. This means that when the electron is, or the wave function we are talking about for the region 2. Time-dependent Schrodinger's equation for region 1 and 3 are, you can see here, these are the time-dependent. We are using the subscript 1 for region 1 and subscript 3 for region 3. That's what we have. We have taken V to be 0 for the region 1 and region 3, and therefore this is the modified form of the Schrodinger's equation in time-independent form. We replace 2mE upon its cross square by k square, where k is the wave vector associated with the electron, and therefore the equation reduces to this: d square psi 1 upon dx square plus k square psi 1 equals 0. And for the region 3, we have d square psi 3 by dx square plus k square psi 3 equals 0. Now, solution to equation 1, as you know that these two are differential equations of second order. Solutions of equation 1 and 2 may be given as psi 1 equals a e to the power ikx plus b e to the power minus ikx, and psi 3 equals f e to the power ikx plus g e to the power minus ikx. Now, this is the term which represents the incident wave in the region 1 traveling in positive x direction, whereas this one represents the reflected wave in the region 1 traveling in negative x direction, whereas this term represents the wave traveling in positive x direction in region 3, and this represents the wave traveling in negative x direction in the region 3. But remember that there is no reflected beam in the region 3, and therefore this term becomes 0, and our equation 4 reduces to this. The transmission probability for the electrons will be given by Ff star by A star, where F star is the complex conjugate of F, and which we can also write as this. So our aim will be to evaluate the constants F and A, which will give us the transmission probability. Now the Schrodinger equation for region 2, we can write as this. You can observe we have not put V0 here because in this case the height of the barrier is V. And we can replace this 2m upon h cross square E minus B by K dash square or K prime square, where K prime is the wave vector in the region 2. Solution to this equation we can write as this, I2 equals this, similar to what we had in equation 3 and 4. Now, one difference we have here, as A is less than B, just look at it, A is less than B, K dash becomes, or K prime becomes imaginary. And therefore we define another wave vector k2 such that k prime equals ik2. Now utilizing this fact in equation 7, we have here psi 2 equals c e to the power minus k2x plus d e to the power k2x. Coefficients a, b, c, D and F can be obtained by using boundary conditions, which are actually continuity of the wave function and the first derivative across both the boundaries. First boundary is here, the second boundary is here. So continuity of the wave function at this boundary demands that psi1 should be equal to psi2. And the continuity of the first derivative demands that d psi1 upon dx should be equal to d psi2 upon dx. Similarly, at the second boundary, x equals L, the continuity of the wave function demands that psi2 should be equal to psi3, and continuity of the first derivative demands that d psi2 upon dx should be equal to d psi3 upon dx. And this is what I have written here. This is. So, all that is required now, at your stage, this I leave for you to do, that you can utilize these conditions in equations 3, 4, 5, and of course 7. You can utilize these two conditions in equation 3, 4, 5, and 7 and evaluate the values of constants, primarily F and A, which is what will serve our purpose. Once you know the value of the constants F and A, you can find the transmission probability, utilize this, use the values of A and F in this equation, and you get the value of transmission probability equal to exponential minus 2k2L. Now observe, if you recall, K2 is equal to how much? This is equal to 2m upon h cross square V minus E and the root. That's what we have. And L is the width of the barrier. L is the width of the barrier. So it's obvious that transmission probability depends upon K2, which in turn depends upon V, the height of the potential barrier, and secondly, it depends upon L, that is the width of the potential barrier. So increasing both the height of the potential barrier and width of the potential barrier will decrease the transmission probability. You can imagine, I can give you a practical example. All of you have studied radioactivity. Emission of alpha particles, beta particles and gamma rays take place from radioactive nuclei. Alpha particles have energy of the order of 4 million electron volt, whereas the potential barriers surrounding the alpha particle is about 28 million electron volt high. Now, can you imagine, classically, it will be never possible for the alpha particle to come out of the nucleus. But it does come out. It does come out. We do observe the emission of alpha particle from radioactive nuclei. Now, how does it happen? How can we explain it? This is what the explanation is. The probability in such cases of transmission of the particle is never zero, unless the barrier is infinitely high. For a barrier of finite length, there is always a probability, though very, very small, extremely small, because an alpha particle has to strike the barrier about 10 to the power 38 times before it is able to penetrate the barrier once. Imagine how small the probability is this, but nevertheless it is not equal to zero. So this is what we have. So this is how we can do this. To conclude the lecture, I give you a problem which you can note down. Electron beam of energy 1 electron volt are incident on a potential barrier 5 electron volt high and 2 nanometer wide. Calculate their transmission probabilities and also find the change in the transmission probability if the width of the barrier be double, first case, and second case if the height of the barrier is doubled. Thank you.